everyone. Thank you for coming to our session. Today we are going to talk about how to use XAI to explain security product. This is a joint work with Kailiang, Xinyu, and Xuguang. And I will start with the motivation to explain how we come up with our idea and why we want to conduct this research. As it shows in the title of our presentation, explainable artificial intelligence, or XAI, is to solve the common issue in machine learning field, which is even the designer of the model failed to explain why the model arrived at a specific decision for a given input. In the academic field, researchers proposed multiple approaches to break this barrier and make the model not black box anymore. In this presentation, our main focus is to use XAI to explain security product. Indeed, our work is not the first one to explore this field. Several works had already demonstrated the benefit of explaining security product. Inspired by those amazing works and combined by the experience in our daily job, we found that there is still a big gap between the academic research in this field and the demandings in the industrial world. We will share our experience to try to fill this gap and share it in the rest of this presentation. There are multiple cases for us to use XAI to explain security product. The most common one is for the security companies to use XAI to explain their own security product, to either provide more insight of the detection result to customers or help their engineer team to improve their production based on the explanation. The majority of the XAI work targeting this scenario, basically they assume the model can be treated as a white box, which means the tools is able to analyze each layer inside the model and also to access the whole training and the data set. In addition to this common scenario, there's another demandings from the industrial world is that the customer of those vendors product or potential buyers, they can leverage XAI to evaluate the product in order to help them making the purchasing decision. Usually, it's conducted by the company's security team. So currently, like the security team will deploy the vendor's product to the company's testing framework and feed malicious and benign samples to the environment and measure the false positive and the false negative rate to evaluate the product. But with the XAI, they are able to further peek inside the machine learning-based security product by checking whether the model's detection result is reasonable or not. So basically, they can generate the explanation of certain samples and evaluate whether the vendor's model capture the essential of those type of attack in the samples. And then it gives the security team a higher confidence to make the purchasing decision. Moreover, we can also extend the scenario to the case that attacker leverage XAI to launch certain type of attack against the commercial security product as well. So with our presentation, we hope the audience can understand what is XAI and how it works in the high level. And also from our shared library, we want to the audience is able to actually use XAI to evaluate security product in their daily job. And also, since we propose a new gap between the academic research and the industrial world, we hope this can inspire researchers to further fill the gap in their future work. And although XAI is a very hot topic in the past few years, but not everyone are familiar with it. we will briefly explain the few common tools available here. So most of them are model agnostic. By model agnostic, we refer the approach to treat the model as a black box. So basically, the model exposes only the function, the prediction functionality to the XAI tool. And the things in our scenario, when we evaluate a vendor's product, the vendor will never release their design detail, like what model they use, what the training set is, and how they extract the feature. So basically, this type of model agnostic tool is a perfect fit to our setup. One of the most popular XAI tools is called LAM, which refers to Local Interpretable Model Agnostic Explanation. The idea of this approach is quite intuitive. So basically, it leverages random permutation to generate a large number of samples around the original instance. Then it invokes the target model to get a prediction result of those random samples. And then LAM trains a local surrogate model, such as a regression model, to approximate the original sample in its local area. At last, the LAM also assign different weights to the random samples based on how close they are to the original instance. So with this local model, LAM can generate an explanation by interpreting the local model on this specific sample. So LAM 2, the library, provides extensions for different types of data, including image, tabular, and text, which is cover the majority of the cases. So in addition, because LAM does not leverage the feature extracted from the original sample set, but the presence of the other set of the entity in the original instance. So it's extremely valuable to explain the model, which is trained with non-interpretable features, for example, common NLP tasks. So although LAM library seems to be promising, it also has a few disadvantages. The first concern is that this tool has an issue to provide consistent explanation for the same sample. This is because it uses random permutation to generate the samples. So it is common that giving a same original instance, the LAM will generate different random samples if you run the tools repeatedly, and which leads to the different explanation to the same input on the same model. The second concern is this sampling process. So basically, the LAM just uses the Gaussian distribution to generate those samples and ignore all the correlations between the features. This leads to a problem that the data point is highly unlikely to be seen in the training set, which means that when the prediction output from the model to those unlikely seen samples is not reliable, which is also compromise the quality of the explanation generated by the LAM. Another state-of-the-art model agnostic tool is called SHARP. And this tool is inspired by the sharply value concept from the game theory, and it calculates the contribution of each feature to the prediction output. So similar to the random permutation step in LAM, SHARP gets the sharply value of a feature I by calculating the weighted sum over all the possible feature value combination other than I. So but the majority different to LAM is how they measure the weight of those random sample when training when generate the explanation. LAM use the distance as the weight, but SHARP use the collision vector. So the larger or smaller value will get the largest weight. Based on our high-level introductions of XAI tools, I hope most audience here are able to capture the rough idea on how XAI works. Now we are going to evaluate different types of security products using those tools. Theoretically, since we use model agnostic approach, we should be able to explain all types of security products. The only limitation is the input type, because not all the security products come with the numerical feature. Some of them use the non-numerical feature, which is make it harder to explain. The first security product we would like to explain is the malicious HTTP request detector. It can be used to analyze the traffic and identify the malicious or suspicious activities. The attackers are able to craft a request with malicious code embedded in it, either as a plain text or encoded format, so that they can launch attacks such as command injection, SQL injection, or cross-site scripting. Our goal is also quite simple. We generate an explanation of those products on several malicious headers and check whether the product identify the injected code section on making the prediction result. Ideally, a good model should assign higher weight on those injected code section in their explanation. Another thing we want to emphasize of this type of product is because unlike a majority of the security products which leverage numerical features as input, the input of this product is the raw HTTP header, which is in the text format. So the product may need to leverage NLP technique to convert the text to a latent embedding before feeding it into the model. This makes the explanation process a little bit different, and we use LAM text module here to explain this model. In the official LAM library, users just need to pass model's prediction function, and then the library will invoke this function to get the prediction result of each random generated permutation samples. However, there's no such a prediction function exposed by the real security product. In order to get the prediction score, we have to craft a real HTTP header and generate the traffic by sending those contents to the network interface monitored by the product, and retrieve the result from the product's log or dashboard. Therefore, we customize the LAM library to make it work. Firstly, we implement multiple adapters to convert the permutation samples to a real object. It depends on the different type of product input. In this case, it's the network activity, but in other cases, it could be binary files, even cloud service API calls. We also redesign the current LAM library to support this type of a prediction function flow. Since comparing to the traditional way, this type of flow takes a much longer time, and we divide the LAM library into two different parts so that we can achieve this like the asynchronous way to generate the explanation. Besides that, there's another thing we want to emphasize using this example is that remember that we mentioned the disadvantage of the sampling process using by the LAM. Basically, just ignore the correlation between features and randomly generate the samples. In our case, the security product's input is highly structured. Taking the HTTP header as an example, so the header need to be valid in order to feed several different kind of restrictions. And but when we use the original LAM library, it just randomly generates the samples, and the majority of them are not even valid. For example, it can be the case like the header is missing, some header field is missing, even the request, the GET request come with some request payload, which is all the invalid headers. Since those invalid headers are rarely seen in the training set. So the prediction result come with the model is not reliable, and which is compromise our explanation as well. So to mitigate this issue, we extend the LAM library by adding the module to replace the random sampling process with the structure of awareness sampling. So as a result, our customization not only improve the speed of the tool, but also the quality of the explanation. And this idea can also be applied to other type of input, like a binary file or the cloud service API call. So let's move into the actual explanation we generated from this model. And the first test case is the malicious header come with the cross-site scripting attack, which embedding the encode the script into the base 64 format. So from the evaluation here, you can see that the prediction result is correct, and also this malicious payload, also have a higher score contributed to the malicious score. So basically, using this example, we have a higher confidence to believe the model capture the essential of this type of attack. Another case is the SQL injection. Basically, from the domain knowledge, we can say we know that this all 1 equal to 1 is the malicious part, and the prediction result is correct. And but the highest weight of the explanation is not this 1 equal to 1 part, although it still be part of the malicious contribute to the malicious score, but this case is weaker than the previous case. Basically, it's just okay for this model to capture this kind of a SQL injection attack. And the third example is the cross-site scripting with the plain text JavaScript code. And this piece of Java code just will invoke the document.write function and inject the iframe. And so the model predict this header correctly, mark it as malicious, but the highest weight is the request payload header field. It's not actually the part of the code, the JavaScript code. So even the document part of this code is contributed to the binary score. So this kind of evaluation can tell us this model or this security product is not quite able to capture this type of attack. And the last attack is the XAI DOS attack under Unix server. And also we put the malicious code into the request payload. And in this type of attack, similar to the previous example, some part of the code even be contributed to the binary score, and which makes us kind of suspicious to how this model capture the essential of this type of attack. So that is the first model. So with the same type of tool or technique, we are able to detect the other type of attack. And this type of attack is also captured by the different academic work. Next, Kailiang will present other interesting findings during our research.
So as a security product buyer, they are not only interested in know the performance report of the security product, they also want to know whether the security product they are going to buy will going to solve the problem that they care about. So we think instead of explaining the individual example, so we should provide a concept level explanation that better evaluate the security product. So in this presentation, we're going to use the malware detection model using system call to explain our point. So system call malware detection collect the system call usage from the individual process. Then they fit all this usage to the ML model to detect whether the usage has any malicious pattern. To basically illustrate our point, we manually crafted two global concepts, CQ injection and the command injection. For the CQ injection, we think it has the following usage pattern. First, it has high file usage. Second, it should have high memory usage. The third is it has high network throughput. For the command injection, it has high the execve usage. So we use a tool called TCAV to elaborate our concept on one the system call security product. And as you can see from this example, the system call have significant the score for this secure product, and the command injection has very low score from this output. Although both concepts receive very high performance usage, you can see that in reality, there's for the command injection, it has a strong gap between the human knowledge and what actually the machine learning model it learned from. So by doing this evaluation, we also realized that we searched in the market and we did not find the concept level, the XAI tool that can work on the black box model. And using these TCAVs, we have to fit this as a black box model and need to know the layer information. So we think that this could be a gap that a future academic work trying to fill in to work on the black box model for concept level explanation. Next, we're going to shift our angle to be an attacker. So as an attacker, we're going to achieve the following goals. First, we're going to use XAI to craft an adversarial example. And second, we're going to use XAI to leak information from the security product. So to craft an adversarial example, so the traditional approach is to minimize the distance between the adversarial example and the actual label that the attacker trying to get. And there's mainly two types of approach: white box attack, which is trying to get the weight of the model and trying in order to calculate the gradients, and the black box model, which create a segment model, and the segment model is similar to the actual the security model. However, to train the segment model, it requires tons of data. So we think both of the attack is not practical for us to exploit the security production because we cannot extract the weight from the security product, the AI model, as well as we don't have tons of data to train a surrogate model for the secure product. So the restriction for us to generate the adversarial example is to satisfy the structure information, structure requirement that can still be fit into the secure product, as well as it need to be keep the malicious behavior. We use the intrusion protection system to illustrate our point. So this is the one example, one HTTP request that we found out. Although the ML, the secure product, protect this as a correct malicious query, but it does not actually learn the right places. So it did not learn the actual the CQ injection pattern. So we think that we can leverage this example to generate our adversarial example. Here is how we do it. So we find one not malicious, basically the benign behavior from the example, and but the model predicted as malicious, and we just modified that field to be a benign pattern. And we found out that by simply changing the high weight patterns, then we can get adversarial examples, then they can pass the IPS, the detection. Here is another example that we use XAI to leak information from the hyper-secure product. As a hyper-secure product, it is mainly the high-level idea is to using a list of heuristic rules plus the AI models to predict the secure behavior. So we intentionally modify one secure product to include heuristic rules, all 1 equal to 1, which is a secure injection pattern. And what we found out is the alarm tools can stably and accurately identify this out. We tried multiple times, and every time it can give us a very high confident score for these rules. So we consider as attacker, if they can learn the rule from the secure product, it is information leakage, and the attacker can leverage that.
At the end of the presentation, I want to appreciate all your attention. If you have any questions, please feel free to ask in this part.